Hello, good afternoon. So this session is the Dork Arts, forecasting and prediction. I love that name. I should say up front that this panel is sort of like an organ transplant patient who's had too many organs transplanted out and is essentially now a different person. So I am replacing the moderator, and we have two of our four original panelists and two people who agreed to fill in at the last minute. So very appreciative, and we're going to be kind of winging it a bit and having a little bit of fun. My name is Carolyn Johnston. I am a consultant with Dev Global. And so without further ado, let's go ahead and get started.
Good afternoon, everyone. I'm not Raghu Ganti from IBM Research. I'm filling in for him. Unfortunately, Raghu had last-minute illness and he could not be here. So I'll try my best to cover his slides and cover the material that he was going to talk about. The good thing is this is the work that we're doing with him. So I'm actually Rahul Ramachandran. I'm from NASA Marshall. I lead a data science team. And we've been working with IBM Research on this really exciting topic in AI called foundation models. So if you've not heard of it, foundation models are these pre-trained models on large unlabeled data sets. And the way they are constructed takes away the need for having lots of training data for them, right? So they work with any kind of sequence data that you can construct your deep learning networks on. And the nice thing about these models are if you train them on large enough data sets, the model can be generalized enough to be utilized for many kinds of downstream tasks. You've seen this example in the natural language area. In fact, this is a graph that's showing the self-supervisation at scale. And the change in the scaling came about with the advent of this transformer architecture, which has allowed to go to millions of parameters in terms of the model size. And the nice thing about it is that the model can then be used for multiple different applications, not just one particular application, the way we traditionally build our models. The exemplar is in NLP. We've seen the examples with BERT and GPT-3, where you can do this Q&A kind of benchmarks, where you can give the model a paragraph and ask questions, and the model will return the answers. And what has been found is that these models, even though they don't have to be really big, they can beat the existing benchmark of human accuracy by at least 30%. So that has shown phenomenal potential of use for downstream tasks. So clearly, you can leverage the same approach beyond natural language processing. You can apply to different kinds of data, time series data. This is the work that has been done by IBM Research. They've applied it to tabular data, chemistry and materials data sets, and also to programming languages. This is an example this is an industry example of using time series data and building a transformer-based foundation model. And what they've found is that for many different downstream applications, going from regression to classification, they see marked improvement in the accuracy and lowering of the root mean square error by using this approach. So what really got us excited was, we know with remote sensing, we have this two major issues. There's lack of large training data sets. Actually, the keynote when we started SatSummit, Ahmed mentioned about this training data set issue and how they're creating this ML hub for this training benchmarks. This can actually address that issue by if you can build these foundation models on optical remote sensing data. You don't need large training data sets for your application. You can actually fine-tune a foundation model for your
uncertainty, you could actually say that, I think I see there is a Walmart being built. And David, there was an award-winning paper back in 2004, and the work was done in 2006-ish and then 2008. So, but what made me think is that, it was a pretty good success at the time, but, 15 years later, the question is, can you predict? We never looked at, could you predict when the next Walmart is going to be built? Okay. And I think that's a fascinating challenge. I don't think we have solved it quite yet, but that's what would be worthy for the community to collectively look at, is not just physical processes, which are relatively easier because, crops grow, so you can reasonable certainty say, the vegetation is going to change in particular. And if you think about the Modi sequence, at some point of time, some pixels are pretty predictable in the Midwest, and when snow is going to come in based upon the time. So physical processes are easy, but the hard ones are the human processes, and this gave me a opportunity. So what do we really want to do with this? One of the things that we do for the community is we increase our insights and understanding of distribution of human population on the surface of the planet. And it's really trying to forecast where are people going to be. And part of that forecasting relies on very robust forecasting of land use, land cover change. And I think if there is a grand challenge that I would like to get onto, it is global scale land use, land cover change, because it has profound significance on our efforts to model climate processes, because it's a triangle with humans, land use, and climate on each corner. As climate changes, it changes land cover, it forces land use, it makes people move, and that enforces land use, which feeds back into climate models again, right? So it's a pretty significant challenge. So if there was a forecasting and prediction, it's the intersection of physical processes with human processes, and that's a pretty compelling, motivating thing for the community. What's next?
All right, I don't want to spill my coffee. My name is Subit Chakrabarti, and I lead the technology team at Cloud to Street, which is a flood mapping company that works with the World Bank, the World Food Program, and insurance companies, and a lot of kind of like on-the-ground agencies to help communities prepare for flooding, get alerts when there's flooding, respond to flooding, and recover from flooding. So this is the kind of like disaster life cycle that Ritvik showed yesterday morning. So that's the same thing. A few years ago, David, same David, by the way, that Budhu was talking about, my boss told me, like the easiest job in remote sensing is detecting water. And I was like, well, I found my next career move. Turns out it's like not easy at all. So we use satellites with AI and local intelligence, and we use all the satellites that you are very familiar with, including Landsat, Sentinel-1, Sentinel-2, Capella. Thanks, guys. And Umbra as well now. So, but we usually just like look at kind of like single images, and we build convolutional neural networks to detect water. And the training is through kind of like manually annotated, like human annotated labels. Although Nana tells me I should use transformers, and maybe we should, seeing Rahul's presentation, it convinced me. So our kind of like bread and butter is just kind of like looking at sequence of images and detecting flooding in those images with super high accuracy. And we also, have tried to incorporate hydrologic states from land surface and hydrology models into our CNNs so that they can kind of like see through clouds. And all that's really interesting, but it's not forecasting. forecasting is really difficult. We do monitoring. But all of our customers, whenever they talk to us, want us to do forecasting because it's such a visceral thing, right? Like, if you could forecast that your house is going to be flooded, that is amazing. If I could forecast that I would drop salad dressing on my shirt today, I wouldn't have worn the white shirt. Good forecasting can really change people's decisions. So this year earlier, a group of nations in Africa, led by ICPAC in South Sudan, came to us and wanted us to forecast flooding, essentially for early payouts. So, something that I have learned in the last year is that it's always cheaper to prepare for a disaster than to respond to a disaster. So it's cheaper to give money to a village to buy a boat to evacuate than to rebuild the village or pay for the human cost once a disaster has happened. So the system that they want to implement is you have a let's say a decade, so like a 10-day forecast, and there's an index as the one you see on the right, and there's a trigger, and every time the index causes the trigger, you have a payout. Not a large amount, but enough to kind of help the village buy a boat. And we were like, sounds easy. We know scikit-learn. We can just put some forecasts and forecasted climatology, meteorology, and try and build a model. Guys, it's super hard. Turns out, spatial CNNs don't generalize well. Temporal CNNs don't generalize at all. So we used historical precipitation, we used forecast precipitation, but we were getting really terrible model results. And what we realized is when you look at the hydrology of the region, there's a huge wetland in the middle of the country that acts as a buffer for water. So when the wetland is full, then the flood starts to happen. So so you have to characterize the wetlands somehow. So then we started to use gravitational anomalies from grades, which none of us had used ever before. So it was a huge challenge. And we put it into an LSTM. And now the question is, how do you train the model? Okay, the country is completely flooded, or completely cloudy. So you can't have human annotators. So what we decided was to use land surface temperature and use the difference between the day and night land surface temperature to kind of have a proxy for where there is flooding. And that sort of worked. So in some cases, it works really well. On the left, as you can see, this is a 2-week forecast. So every day we look 2 weeks ahead. On the right, you can see another administrative region, and it's really bad. So what we found out was that if you're looking at a certain class of flooding, if you're looking at flooding that's driven by snow melt from the upland regions, upstream regions, you can kind of model it pretty well. But if you're looking at convective precipitation events, you cannot model it at all. And we were like, why is that? Well, it turns out that the weather models in South Africa, in the southern part of Africa, are really bad. All the things that we take for granted here, the high altitude balloons that are assimilated into, the HRRR model that gives an hourly refresh of conditions, doesn't exist in Africa. So of course, we would never be able to find convective precipitation. So I guess that was our experience with forecasting. We need much better models in every part of the world to kind of enable this. But if we are able to do it, guys, that will be amazing. It will really help people. And it's really what people want. So I hope, this is not a solution. This is a challenge. Let's make models better. Let's make label training data better. And, together we can come together to improve what we're doing. Thanks.
Okay, so I work at IFPRI, International Food Policy Research Institute. This is part of CGIAR, it's a global, a lot of acronyms, Global Agriculture Research Network. So yeah, I'm going to talk about 3 cases where we use Earth observation and geospatial data to kind of drive data in our forecasting, modeling, and prediction work. So all the context is about global agriculture food security. So the first use case is what many of our centers, sister centers do, the when, where, when, and how much crop production is happening and should be happening at the end of the season. So in this case, actually, just like a flood, in agriculture field, rice is, we just make a joke about, it's easiest one to predict and monitor because it has flooded land. But it's not always the case. There are so many different types of rice production systems, so it's not always easy to detect and model. But anyway, so there are better ways to monitor or delineate rice production areas than other crops. So in this case, we are in the middle, there is something called ORISA, which is a process-based crop model. So we kind of assimilate the microwave remote sensing data into the ORISA model so that we can make kind of in-season prediction of the crop, the rice production at the end of the season. Our main kind of customer or client, user of this system is government. It's a Ministry of Agriculture or sometimes Ministry of Finance to make a plan for the next year's budget based on what kind of production they are going to expect. So the resolution is not super high necessarily, but it's very important to make consistent kind of output so that they can continue monitoring the system. So I think it's like we make monthly or bi-weekly estimation based on the cropping season. The spatial resolution, I think about like 200 meters or something. But we put a lot of effort, not just on the technical side, but also capacity building, how government can actually embed this system within the ministry. So for example, in this case, a Philippine government, so we totally handed off to Philippine government, and they are now operating by themselves without us involving it. So it's really a successful case in Philippines, and we try to replicate the same model. So a lot of capacity building is involved, and continue upgrading system for whenever there's a new sensor and new monitoring, new data set, as we also work with them to evaluate the performance and improve the system together. The next system is, it's not exactly forecast, it's kind of more nowcast thing. Like for example, the 2015-16 El Nino in Ethiopia, there was a lot of emergency kind of early warning happened. It's not just for Ethiopia, but a lot of African countries were really scared of how much extent of drought, the serious drought will just damage all the crop production. So in this case, we did have some ideas and aggregate level how much production has been lost or reduced compared to normal season. But until very late, we didn't know exactly where and how much crop production loss had happened. But we did have good data on rainfall and weather station data, but we didn't have a way to connect the dots. So we used, again, the crop model to run the scenario through the system, through the modeling system to understand where and how much production loss might have happened to kind of make sense out of the statistics data and also observation data. And in the end, the impact was quite localized. It was a little bit different from what policymakers and people on the ground initially said. But actually, this was quite important information for them to have to target really damages or negatively impacted area to get the assistance timely. The next one is even more macro. So during still going on through the war, a lot of price shock has been happening in the world. At IFPRI, where I'm based at, we have this economic modeling framework running at global level and also regional level and country level. And this is something called computational general equilibrium model. So it has kind of connection of different elements, different components of economy at the national level during the normal year. How much of kind of elasticity between sectors exists. So even if you have a shock in one part of the economy, actually, within some extent, you have a resilience to go back to the normal situation. But in this case, we keep seeing country by country that limit has been exceeded. So we have started seeing the poverty impact due to the increased fertilizer price. Production is getting lost, delayed, leading to poverty and all other socioeconomic problems. So on the right-hand side, you can see the poverty headcount rate. This is our estimation based on what's happening on other side of the story. We can't see it, we can't really observe it from observation or anything until the census and other types of data becomes available. But we can already run the model and make kind of estimation to see where the more targeted support is needed. So that's one of the examples.
So if we have some questions for individual speakers, now would be a good time to ask them. If you want to think about it some more, we'll also have a Q&A period at the end of the discussion. Listening to you talk about your projects, and in particular, Subit, I kind of wanted to establish, okay, we have a good sense for what we can't do and what doesn't work well. And I was wondering, can we talk for a bit about the baseline? What are things that we have been able to measure well using EO data and forecast well, if anything at all?
Yeah, so I mean, it really depends on the window of forecasting. If it's, a few hours to a day to a little bit more than that, I think, precipitation, has been, DeepMind has an algorithm that uses no modeling at all to predict precipitation, a few hours in the future. And I forget the exact time up to which it works, but it, works pretty well. So that's one thing.
So, and then another question for you, Subit. Do you think that that given the appropriate data, the sort of technical instrumentation that we have in the West, if that were available in South Africa, would the application you were talking about have worked, you think? Is it just a matter of the data that you need not being available?
Maybe. I think we have to test to really, I mean, it would be much better for sure. At right now, I can talk specifically about two countries that we have looked at, which is Zimbabwe and South Sudan. The forecasts are not that great. Like, if I toss a coin, I can probably do better. So in that specific scenario, if we had better models, more observations, more weather centers or, weather stations, I think, things would be a lot better for sure. But there is at some point you don't gain a lot more by improving, In the US, I don't know, how much better we could get.
How much better you could get, yeah.
So can I add a few comments here? I think, you can do predictions. Forecasting is a prediction well. You have the right data, and then the phenomena that you're trying to predict is not random, right? If it's completely random, the pattern cannot be discerned in your data. It's impossible to do it. But if there is a certain pattern that can be modeled somehow, and if you have the right curated data set, it is possible to do predictions.
So do you think there needs to be an underlying physical process that can be modeled in order to get good predictions?
If there is underlying physical processes, then the hope is that with the right data sets, you should be able to model it. So if you're building a classifier or any kind of a regression algorithm, you hope your training data set is representing your population distribution so that you can actually model it properly, right?
So Budhu, did you have a comment you wanted to make?
Sure. So I'm intrigued by Subit's presentation. So I think the opportunity here is to move away from thinking of flood as a wet surface, which it is not. The real issue in flood is that right now, flood is a two-dimensional phenomena for us. So all the maps that you see just shows you where water is, but it doesn't tell you how deep the water is. And in flood, that's what makes the difference, is how deep is the water. And the second thing is that how long you will have that depth in a particular location, right? So you go out on Twitter and look at what's going on in Florida. The hurricane has pulled away water from Fort Myers. Like, it's just, there's no water in the streams at all. So it's not just flooding, it's just pulling water away. So these are physical. But Rahul said something that I think is important, which is every physical processes that we know and we feel the physics we understand, if the Earth observation has demonstrated that you can make those predictions better. And we rely on that weather predictions every day, which what we don't realize is that how much Earth observation actually has gone in to make those physical models of atmospheric circulation models and precipitation models that good. Your weather on iPhone will tell you how long before it's going to start raining and when it's going to stop. And it's getting pretty good to our tolerance, right? So I think where we might be having a real opportunity is to understand how the new generations of Earth observation will enable traditional physical models like rainfall runoff models. And it is true that it's geographically varies, but we have never really attempted to do that, right? It's just similar to traffic. We have microsimulations for traffic pretty much anywhere in the Western world. How many people have seen traffic microsimulations for like Africa? We just never have paid attention to it. So I feel Rahul's point is well made, that we need to make sure that the physical processes are not ignored and we are just not driving it from just a pixel.
Can I add just one thing, just the following up on the weather forecast. So what we have been seeing in the agriculture is that higher accuracy and reliability of weather forecast, and also long-term climate forecast, 6 to 9 months, because of the El Nino kind of global climate circulation models are getting accurate. What's really difficult and still quite challenging is sub-seasonal, like next 2 to 3 months. The accuracy is terrible. If you started plotting it, you just don't want to even deal with it. There are still data products, sub-seasonal, the weather, even daily temporal resolution weather data out there, but we tested some of them and none of them are really good. And all the output you get at best is probability that, we have a quick side conversation before the session, really nobody can understand how to act on it. They're having 50% chance of drought for next like 30 to 90 days. What about what to do with that when you want to talk about the decision-making, improve decision-making at farm level? It's really difficult to convey. And so yeah, I think more just better and better accuracy at very short term and long term. I think some really breakthrough need to happen in somewhere in the mid-term climate and weather forecast.
So all done with the commentary on this topic? Ready for the next one?
I just wanted to respond to one point. So yeah, it really, I agree with everyone. I wanted to reiterate that in flooding, depth is more important than extent. Damage is more correlated to depth than extent. And in the US, we have National Elevation Data Set, which is really good. In South Sudan, we use SRTM 30, where the mean uncertainty is 3 meters. That's taller than me. Not actionable.
Yeah. Well, SRTM was great when it first came out.
No, it's great. I mean, having bad data is better than having no data sometimes. But, we have to, local improvements in DEMs is a big thing that I think we need. And a lot of people are working on it. It's not, yeah.
So this may be a good question for Subit and Jawoo. So how about productionizing forecasting? if you basically want to be able to, update your model in order to productionize forecasts and so on, how does that look like in practice?
Yeah, I can talk a little bit more again at the macro and policy relevant level. It really needs to be go beyond forecast. It should also continually update and improve itself so that policymakers and users has a chance to correct their decision if the forecast was not totally relevant or accurate for their location. I made a similar story in earlier session. I don't want to repeat it, but oftentimes we put more focus on early warning and earlier action, but giving very little room for making recourse and the making correction on the decision already made. And usually policymakers are quite hesitant to go back and admit, oops, it was not quite correct, you should do this and rather than that, and that in that case, it's already late. The operationalizing should give enough opportunity for not just for continued forecasting, but giving enough chance to review what happened and giving people to interpret the data and provide that feedback into the system so that it's not just relying on the observation data, also providing human input of what happened and what kind of decision I made so that it kind of evolve itself more in the future.
How do you design a model that can accept that kind of user input?
Yeah, so that's really good question. So I see there are, in computer science side, I'm not expert on it, so I don't know fully how this works, but there is a lot of AI-based causality mining and automated knowledge graph kind of understanding human decision-making processes and trying to mimic that without getting human intervention. I think that's one way we try to make better understanding and maybe even trying to predict what human will make, what kind of decision under what kind of circumstances, and that can also provide more information into the system to train itself. But otherwise, yeah, I mean, it's really difficult to get that level of input from people into the system. And, yeah.
Okay. This may.
Can I add a comment to that? I think I'm supposed to represent the research side in the spectrum here. I think, and from the data science side, I think a lot of us are guilty of, building these classifiers and models and writing nice papers and publishing it, and have very little experience of pushing that model into real world to see how badly it fails. I think that's something that we have to learn, that, the models you'll have to keep iterating on your models even when it's in production. There's always this notion of model drift that happens over time. And you'll get more and more new data that has events that it has never seen before. So you have to retrain your model over and over again. And I think we also have to be realistic about our expectations about the model itself, that it'll never be perfect. It can only do as well as the data it has seen before. So.
And that sort of brings up another question that I was going to ask, which is, and this has come up in a couple of the other sessions, how can we possibly communicate uncertainty around our models? So for example, here's one thing I kind of always wonder, they say there's a 40% chance of rain tonight. What does that mean?
You carry 40% of an umbrella.
Yeah. What does that even mean? Does that mean, what we're told is that over time, 40% of the time that they predict 40% chance of rain, there ought to actually be rain, and the other 60% of the time ought to be dry. Who keeps track of that? And, what consumer group gets outraged if it's 50% of the time, right? So how do we communicate uncertainty at all? Is there a more effective way to do it?
So again, sorry, for agriculture context. We also thought a lot about this because of the probabilistic climate forecast that drove everyone crazy what to do about it. So I think the approach we are trying to take or taking right now is like your example, for example, so you have 40% chance of rain, then if you don't have umbrella or rain boot, you will get soaked. So if you have umbrella and like rain boot and like rain jacket, even if it rains, then the chance of you getting wet is reduced down to like 10%. So the same thing we are trying to do. If there's a 50% chance of rainfall, we don't stop there. We have to translate it to what if that happens, then your chance of losing crop is say 70%. But if you do differently, if you manage field differently, say you build a mini dam or you plant a flood-resistant variety or something like that, then even if that happens, your chance of losing crop is go down to 10%. So that we try to change human behavior based on the potential outcome of that probability. But yeah, it never really worked to change human behavior just focusing on that rainfall probability, for example. So you have to go a few steps further.
Yeah, I agree with that completely. I think that you have to have policy that kind of like, uses the 40% to get to a dollar amount of expected damage that people will then, know what to do with. If you tell them there's a 50% chance you'll be flooded, that means nothing. But if, you tell them, on average, you'll lose $6,000, if you don't do anything. So like having a dollar cost and then having an idea of how much you save if you carry out an intervention, I think is a good way to elicit a response,
Well, I'm thinking about, have any of you lived in hurricane country?
I did my PhD in the University of Florida. Go Gators.
Oh my God, yeah, I went to Florida.
Oh, wow.
we had Florida season. It's kind of, there must be being party right now. Those are cool.
Yeah, so I lived in Louisiana, I lived in Florida. I was in Florida at the time of Hurricane Andrew, and when Hurricane Andrew was just about to come through, we were talking to people in our neighborhood. We had just moved there, and they were like, "No, I don't want to do anything. No, this never happens. Nothing ever happens." And then, wham, and that's just human nature.
Yeah, yesterday on NBC, a woman.
Makes sense to me. Budhu?
No.
Sure. I think there's if you want to. How are we doing for time? We're good.
Is it on? Yeah. So, some of the panels touched on this, the physics and the AI and the data. We see in the climate prediction domain, many people are trying to embed physics into AI very actively as a community, not just a random research paper. But we don't see that in the remote sensing satellite Earth observation. What do you think is the issue? What is the barrier? Why we are not doing it more actively? And as you mentioned, we know the physics. Flood forecasting, we know how river routing works. Why don't we embed them more actively in our AI models? What is the barrier and how we can, as a community, advance?
That's a tough question.
Yeah.
So I guess my background is in atmospheric science. So I think, so from weather perspective, it's easy because you have basic fluid dynamic equations that you can write to model the motion in the atmosphere. I do not know whether you can have something similar for land surfaces, land processes, whether you can write physical processes.
Can I add on to that?
Yeah, go ahead.
So I come from land surface modeling background. That's what I do.
Sorry, you can do it from the live stream.
Yeah, sorry.
You can probably pass this around one of these and we can share. There's only 4 microphones here.
Yeah, but then it gets hard for them.
So
But they can use.
I don't think it's even on. Is it? It is? Cool. It's good.
Okay.
Don't need to double mic. So coming from the land surface modeling perspective, right, we do have a lot of physical models that do all these processes that you're talking about, right? And Subit and I have talked about this before, but when you think about predicting flooding, right, there's a whole field of data assimilation that's been done up to this point using older sensors, right? But now we're getting to planning for the SWAT mission, for example, right, which is going to come online and launch in December. SAR mission in a way. And so my question into that is there value in doing traditional data assimilation right into the land surface models and that community that we already have built around modeling all those things at, NASA, for example, as a first thing before launching into doing it all in AI, right? Because we still have this huge community of people that are doing maybe a little bit old school, but still super valuable data assimilation, right? So just coupling that on, I think there is a field of people that not necessarily interfacing here that could do a lot of work with new EO data. So
I'm going to attempt to answer Hamid's question, because he says, why are we not doing it? So I think why we do anything gets driven by a use case that everybody wants to see addressed, right? So I will predict and forecast that we will see an incredible surge in epidemiological models and forecasting and nowcasting now, because we are all coming out of this acute time when the needs were driven. But there are certain things that I feel that the community has acknowledged for a long time, but have shied away from really addressing it, especially when it comes to physical sciences. When I was in graduate school and first getting exposed to EO and what do we learn about our planet from observation data and measurement, right? So it's not just observation, it's both observation and measurement, because we have active remote sensing. Even if you take something like flooding, one of the very underlying, or food, underlying data element is soils. I would love to see a predictive model that will give us a better soils map. What's the state of the art now? I have not looked at. What is the best resolution soils data for the world? 250 meters? That's
Polaris in the US.
Yeah.
Polaris, yeah.
Yeah, that sounds very impressive to me. 250 meters.
But a lot of accuracy problems with that, right? And you don't know how drainability works with that. I mean, in many places, it depends on the underlying.
So I think, so you're hitting that right point, right? So one of the opportunities that we have now with neural networks, whether you want to call it machine learning, AI, large computers, large data, is we can run many scenarios and simulations to understand the spread of what the world's soils data at 20 meter or 25 meter resolution might look like, right? That would be a good start, just to put something out, and as you said, uncertainty. The scientific community can put focus towards that, which, you have to start somewhere, right? If we could send samplers every point on the planet, then we would not be having this conversation at all. But I think that's a worthy thing to attack from a forecasting point.
So I want to go back to your point. I think that's great. I did not know about, there is an assimilation data on the land side too. I know in climate, the simulated data are used as benchmarks for the models for them to beat, right? So using them for doing your predictive modeling is a perfect data use case there. I think Ahmed was asking, can we embed physics in the AI model itself, which is where, I don't have the expertise to answer that. It's something that I've not looked at, but I think it's an intriguing point.
I think Vipin Kumar at University of Minnesota is doing that.
I mean,
You should look at his work.
We have worked with some of it, which at AGU, there's like a great presentation. We haven't embedded energy balance or mass balance equations into the CNN, which is also possible. It's just very hard. But what we have done is the next best thing, which is take states from NOAA MP and other kind of like assimilated land surface models and put them into the CNN and use them to kind of like improve the temporal resolution of what you can get from satellites. And that works pretty well in the US. Outside the US, there's obviously like data problems and stuff like that. But because you need a lot of auxiliary data, you need like flow direction, flow accumulation, soil texture, like a lot of other stuff. If those were better outside the US, the predictions would probably be better. But yeah, I think the next thing which I commented on is like using a layer in your CNN that essentially enforces the mass balance of like water flow. Like that would be really interesting.
You have a...
Oh, hello. Hi. Caitlin Howarth from Yale Humanitarian Research Lab. Budhu, you're the man. That came explicitly from Chad to you. Budhu is the greatest. He and his whole team at Oak Ridge have been like in our corner since day one. And just want to say hats off to you. Thank you so much.
It's all because of David.
So who is David?
He's now left.
Oh, he left? Okay.
Left the room. Not left, but left the room.
So the example has been brought up a few times of South Sudan, probably one of, if not one of the hardest places in the world to work due to conflict. As you know, weather data is battle tempo data. How would you propose to move that data, especially as it's being enhanced, as fast or faster into the hands of those that are using it for positive impact and agricultural development for ways that actually generate peace and sustainable, are going to be moving it to reinforce their understanding of the fighting season?
That is probably the most difficult question asked today. I think we need to have a framework of ethics around like who we give data to, who we don't give data to. Obviously, as a commercial organization, we do have that internally, and we have faced it not in South Sudan, but in Mexico, where, Beth Tellman, who like a lot of you know, has worked on kind of like land cover land use change, which, can uncover narco trafficking routes and stuff like that. So we have our internal ethical framework that we use to decide whether to give the data to someone or not. Like usually we do a vetting process, but the data that we consume to do our modeling is freely available and can be easily accessible, to those who have nefarious purposes. And I think it's up to the organizations producing it to have a framework that they use to decide whether they let people access the data or not. But yeah, we have our internal ethical framework. I don't really know. Maybe these guys are more in a position to answer.
I agree that it's a hard topic, but I can introduce another level of complexity that usually do not get discussed at these meetings, but some of the meetings that I'm at, which is how do you know that the pixel that is coming to you is actually true? Okay. We hear about ransomware, which means somebody breaks into your system, keeps you hostage till you pay. But don't forget that the satellite constellation system and the entire process is as vulnerable as your banking system. So there are many reasons different countries would love to change some other country's view of the world or even themselves, right? And it's not just it's the unethical issue that we will eventually deal with. And in the intelligence community, they call it geo-intersurance. That how do you ensure that the pixel that was actually captured, and by the time it came, it was never touched and manipulated and changed, right? We need very robust AI-driven approaches to ensure that, Rahul, you were talking about predicting, right? What would be the next one? So there are some work that's going on about trying to understand those kinds of larger level ethical things, that doing forensics to understand, is this true, what it's out there or should be out there or not. In terms of sharing, that's always is going to be, a key question that is always the community grapples with. You all are witness to how the open source or OpenStreetMap community stopped updates during the Ukraine crisis because they were not sure that it's the Ukrainian who are benefiting, but it could be used in adverse mode by the adversary. So it's a tough question. Best.
This is a question about the perception and the challenges that early warning system providers have with their models, ML or physically based. So particularly for crop yield prediction, are you, I'm sorry, I don't have your name at the far down, but for crop yield prediction, are the early warning system providers, IFPRI or related organizations, more comfortable with physically based approaches or ML models?
So yeah, usually both. And this is also where we really want to make sure the users, the policymaker, understand the kind of probabilistic nature of any model prediction that we are making. So yeah, both. Usually the reason also we are trying to make it embedded in the government is they can let people go out the field and make sure this is really what's going on in the field. Yeah, a couple of years ago, we had a case in Kenya. We thought the crops are not being planted maybe because of COVID or farmers are sick. And yeah, there are a lot of early warning, kind of early alarming happening within the organization. But what turned out to be when we actually asked people on the ground, it was an incredibly wet season in between seasons, so during the fallow season. So there's just no changes in DBI between fallow and cropping season. So if we hadn't had that, local knowledge, local people saying, no, I mean, everything's fine. It's just, we had a really wet fallow season. Yeah, we could have made really miscalculation of what could happen. So yeah, there is always really difficulty of making just model-based predictions. So you would usually go with the knowledge.
Okay, we have only a couple of minutes left, and I thought I would just ask a question, perhaps directed mainly to Budhu, but to all of you. What trends do you see that are up and coming? What are we likely to see in the next few years in terms of prediction and forecasting from EO data?
I think land use land cover is a very impactful and right target. I think there needs to be a community-driven effort in making sure that we have a very robust way of predicting, forecasting land use, land cover change, because that influences so many different things and so many different applications. So that's, and I'm particularly encouraged in the wider interest of the community where we are collectively building, knowledge. So you could, it would be good to see where a global model is being built globally, right? That you have local people, as Jawoo said, that local knowledge that needs to get into these kinds of models. That could be a fantastic thing to have in the future.
So I would, I'll go to the slides, Raghu's slides on foundation models. I think the potential there is immense. If you could train a foundation model on one optical sensor, could you apply it on other sensors from other instruments? And it removes the burden of having large amounts of training data sets. And the other thing we have to validate is whether the model is is generic enough. It's it's not. One of the issues with machine learning is the model tends to be very localized. Is the foundation model generic enough that can be reused across regions? I think those are the opportunities here that we can potentially leverage.
Yeah, I think it's integration of more physics into machine learning. I think, when you have a purely data-driven model, how can you predict what a 100-year flood looks like when you have never seen a 100-year flood in the satellite record, right? But if you can integrate, our physics-based understanding of how water flows into the model, then suddenly your, extrapolation becomes much more realistic. So I think that's the next big thing.
Yeah, I want to second Budhu about the land cover modeling, land cover also mapping process becoming more precise and more detailed. So we currently have 9 classes from dynamic world, but I really want to see like 20 or 30 or 40 classes giving more detailed information within those aggregate classes so that the local information can be also incorporated and kind of predicted at more higher resolution.
I heard Regrow is working on that.
So, and we are at time, so we'll finish up. Thanks very much for attending.
Thank you.
How much I adore